In section 10.2 of chapter 10, we're going to be looking at ellipses. Now, ellipses are another type of conic sections. Basically, they look like elongated circles, or what we might in common language refer to as ovals, but they have a very specific mathematical definition, and they fit in the context of this larger group of curves known as conic sections. And we're going to start this section by defining exactly what a conic section is, so you can see a picture of why they are called conic sections, and then begin looking at the conic section, starting with the ellipse. To begin with, let me point out that conic sections, by definition, are curves that result from the intersection of a right circular cone and a plane. So conic sections are curves that result from the intersection of a right circular cone and a plane. So let me show you an illustration of what that looks like. Now, in your notes there, you have a picture of this condensed into one or two cones, but let me look at them one at a time. Okay, so you see, for a circle, if you were to take a cone, now mathematically speaking, a cone is actually both the bottom half and the upper half, and this thing extends on forever, both upwards and downwards. That's a mathematical cone. If we were to take just a flat plane and intersect that plane with the circle, where the outside of the cone intersects the plane, is going to be a conic section. Conic intersection, right? So if I did the plane straight across this right circular cone, that shape that you see right there, if you were to look straight down on that plane, is a circle. Why? That's why the first curve that we looked at in this chapter was the circle. It was a conic section. Now, if I slightly tilt that plane sideways, what's going to happen is that shape is going to stretch out in one direction, right? It's going to become more ovular, right? It's going to look more elliptical, which is going to be the ellipse, what we're going to talk about in this section. Now, if I kept going so that the angle or the slope of this plane was equal to that of the edge of the right cone, the shape I end up with is a parabola. Okay, it's got this bending shape to it. And if I kept going vertical and went straight up and down, that shape is called a hyperbola. Now, hyperbolas have actually two pieces. They have the upper piece and the bottom piece because you're intersecting both halves of the cone. And even though they look similar, like the parabola and the hyperbola look similar, at least on the top half, there is a distinction between these two shapes, and we'll come back and talk about that in the section where we cover hyperbolas. So let's begin with talking about the ellipse. Let me point out real quick, though, that there are some interesting applications that we get out of conic sections. Applications in the real world. Now, we're not going to have time to go through a whole lot of these in detail in a class like this, but if you were to take a physics class, for example, you would see a lot of these types of applications showing up throughout that course. For example, the movements of planets are conic sections. Okay, one of Kepler's laws says that the motion of a planet about a body such as the sun is the shape of an ellipse, where the sun is at what's called the focus of the ellipse. Bridge and tunnel construction. One of our application problems we'll look at in this section will be dealing with bridge and tunnel construction. Navigational systems, being able to navigate on the globe. The manufacture of lenses for telescopes, or even lenses for your eyeglasses, and a procedure for disintegrating kidney stones. That's an interesting application that shows up using parabolic shapes. Even if you have a direct TV or satellite dish, there's an application of conic sections there, because the cross-section of one of those satellite dishes is in fact a parabola. And that's just one of the types of conic sections that we deal with. The formal definition for an ellipse is given as follows. If you have 2 points, which are referred to as foci, which are the plural of focus, right? You have 2 foci, each one is a focus of the ellipse. The set of all points such that the sum of the distances to the foci is constant is called an ellipse. And like I said before, it looks like an oval. So from this definition we get kind of a geometric interpretation of an ellipse, right? So let's say this is the shape of my ellipse. The foci are a couple of points in here, right here and right here, so that every point on the outside here, if I were to measure the distance from this point, which I'm calling a focus, to a point on the outside, and measure the distance from that point to the other one, if this was, say, distance 1 and this is distance 2, if I were to pick any other point on the outside, say I pick this point, just an arbitrary point out there, and did the same thing again, took another distance from and another distance here, called this D3, D4, right? The sum of the distances from the outside point to each of the foci, D1 plus D2, is going to be the same if I do it for any other point, D3 plus D4. Okay? That sum of the distances to the foci is constant for any point on the outside of the ellipse. The equation for an ellipse that is centered at the origin is given in its general form, looks like this. It's x squared divided by a squared plus y squared divided by b squared is equal to 1. You get it equal to 1 on the right hand side, and you can interpret from the left hand side some information about the ellipse. The number that's divided into the x squared term, right, the square root of that number is the, and I'll put it in quotes here because it's not a formal term here, but we'll call it the radius in the x direction. And b is the radius in the y direction. So if an equation is given to you in this form, you can recognize, one, that it is an ellipse, and two, you can determine the shape of that ellipse. You can graph this thing on the Cartesian system. Let's do an example. This equation is the equation of an ellipse because it has this form. It has a square in the x, a square in the y, and they're added together, and you have 1 on the right hand side. So from that we can now determine that, one, it's first of all, we know it's an ellipse centered at the origin. So looking at this thing on our Cartesian system, we know the center of the ellipse is right here. Now the number underneath the x is a squared, which means a is the square root of 16, or 4. That is the x radius, meaning that's how far out in the x direction I go. I'm going to go 4 left and right, 4 this way and 4 this way, to reach points on the ellipse. Okay? B squared is 9, so that means that b is the square root of 9, or b is 3. So I'm going to go up 3. I'm going to go down 3. Okay? And then I'm going to connect that with my oval, or ellipse shape. That is the graph of that ellipse. So all you got to do is find the a and the b by taking the square root of the numbers underneath the x squared and the y squared. And then go, the a direction is the x direction, the b is the y direction. Now consider what happens if, for example, the right hand side is not 1. I still have an x squared and a y squared, and they're added together. That's a key for this thing to be an ellipse, but the right hand side is not equal to 1. So how might I get that equal to 1? The easiest way to do that is to divide by whatever number it is. Divide that by itself and you'll get 1. But if I divide it on one, I got to divide on the other. So what I'm going to do is I'm going to divide everything by the right hand side. Divide by 400 to get 1. So we'll get it in our standard form. X squared over a squared plus y squared over b squared equals 1. If I divide this by 400, this by 400, and this by 400, and reduce my fractions, I'll have something in standard elliptical form. Clearly the right hand side is 1. Now what about the x squared? I've got a 100 on top and a 400 on bottom. 100 goes into both of those 4 times, so I have x squared over 4 plus. 25 goes into 25 once and goes into 400 16 times. So I end up with y squared over 16. I'm just dividing top and bottom by 25. Just 25 goes into both of them. Now I can identify the a and the b. A is the number that's squared that gives me 4. So a is 2, or the square root of 4. B is the square root of 16, which is 4. So now I can graph this thing. It's centered at the origin, so I go 2 left and right, and I'm going to go 4 up and down. And there is the shape of the ellipse given by the original equation. Now, I mentioned this earlier, but the shape of the planet's orbit about the sun also forms an ellipse, right? So we recognize that that shape has an application. Now, what happens if we're not centered at the origin? What if we're somewhere else in the Cartesian coordinate system? Well, we can modify our formula for the equation of an ellipse to be centered at the point h, k. The only difference now, instead of x squared, we have x minus h squared over a squared, plus, and instead of y squared, we have y minus k quantity squared over b squared. Still is equal to 1. So notice how this is very similar to what we saw before, even with circles, but now we got to identify the h and the k to get the center of the ellipse. So we got to identify h, k, a, and b in this problem. So first of all, let's do the center. Don't forget that when you're doing the center, you're finding the h and k, and they're inside these squares, right? If they're inside a square like that, you have to take the opposite sign. So that's a negative, so that means positive 3 is my h, and that's plus. Since the formula has a minus in it, that means the k is a minus 2. So there's my center. Now find the a and the b just like I did before. A is the square root of 4, or 2. B is the square root of 9, which is 3. Now instead of going from the origin to graph the ellipse, I first find the center. I go over 3 and down 2, and from this point I'm going to count out my x radius and my y radius. I'm going to go left 2, I'm going to go right 2, I'm going to go up 3, 1, 2, 3, and down 3, and draw my elliptical shape. Now we'll do one application problem involving ellipses, and it's the application I mentioned earlier where we might have bridges and tunnel construction. Okay, in this particular case, we have a semi-elliptical archway. Semi just meaning half of the ellipse is the archway over a one-way road that has a height of 10 feet. 10 feet right here, and a width of 40 feet. Our truck has a width of 10 feet from side to side and a height of 9 feet. The question is, can we get through the archway? Now, to answer that question, we're going to find the equation of the ellipse and then use some algebra to answer the question. So let's start by determining what the equation of the ellipse actually is. Okay, going back to our formula for the ellipse, x squared over a squared plus y squared over b squared equals 1. That's for the ellipse centered at the origin. I'm going to use that one because I'm going to put my origin at the very center of this ellipse. Okay, so here's my tunnel. I'm told that this width here is 40 feet. So what's my x radius? Clearly that's going to be half of that, so that's 20 feet. Now the height would be the b, or the y radius, which happens to be 10 feet. I'll just put a dash there for foot. Okay, which means A is 20 and B is 10. If I plug that in up here, that means I have the equation x squared over 20 squared, 400. Right, that's just 20 squared. And y squared over 10 squared, for b squared, is over 100, is equal to 1. Okay? Now where's my truck? My truck is 10 feet wide, right? So I'm going to put him 5 feet on either side of this, like this. So this distance here is 5 feet, this distance here is 5 feet. Now how tall is the truck? It has a height of 9 feet. The question is 9 feet going to fit underneath here, or is 9 feet going to be somewhere up here? Right? We know it's not bigger than 10 feet, but we can't really tell just by looking how fast this arch is going to fall down. So the question is, how high is the arch right there? We know how high the truck is. How high is the arch? So here, right here, would be the value for x equal 5, right? At a height of, at x equals 5, because that's right 5. Actually, I could even plug in negative 5 if I wanted to. The question is, what's the y that goes with it? What's the height of that point on the ellipse? So we're going to let x equal 5 in this equation, plug it in, and see what the y is that goes with it. Right? Does that make sense to you? I hope so. If not, you certainly want to either rewatch this or email your instructor for more, to ask some questions. Plugging in x equals 5 gives me 25 over 400 plus y squared over 100 equals 1. To solve this for y, I'm going to multiply both sides by 400 to get rid of the fractions. 400 times everything gives me the following. The 400 times the first fraction cancels and leaves me with 25, plus 400 times y squared over 100, the 100 and the 400 divide out and leave 4, so I have plus 4y squared is equal to 1 times 400 is 400. If I subtract 25 across, that gives me 4y squared is equal to 375. Dividing both sides by 4 gives me the following. The 4's cancel, so y squared is equal to 375 divided by 4 is 93.75. Take the square root of both sides, y would be 9.7. And it's positive because we know it's going up. It could also be negative, but negative doesn't make sense in the context of this problem. So does the truck fit? Well, the height of the ellipse 5 feet over is 9.7. So yes, the truck will fit because the truck was only 9 feet high. So this is an example of where we can use our knowledge about the ellipse to find the equation and then answer a question about the height of the ellipse at a certain point. Okay? All right, that's the end of section 10.2.